You can survive almost anywhere on Earth. Arctic ice where temperatures drop to 60 below zero. Deserts where a year passes without rain. Mountain peaks where every breath contains half the oxygen your body needs. Dense rainforests, open grasslands, coastal shores. Your ancestors didn't evolve different bodies for each of these places. They had the same biology you do, the same hands, the same minds. Yet somehow, within just 50,000 years, Homo sapiens spread from tropical Africa to every environment on the planet, thriving in conditions that would kill nearly any other large mammal within days. How? Not through being stronger, faster, or more physically adapted than the specialists. A polar bear will always survive Arctic cold better than a human using biology alone. A camel will always handle desert heat more efficiently. But that's not the comparison that matters. Tonight, we're discovering why Homo sapiens became the most adaptable species on Earth, not through superior bodies, but through something far more powerful. Minds that could change without waiting for bodies to evolve. Culture that transmitted solutions faster than genes ever could, and cooperation that multiplied what any individual could achieve alone. We'll explore how behavioral flexibility let humans adjust to new environments within lifetimes rather than waiting thousands of generations for genetic evolution. How a discovered technique could spread through a group in weeks and pass to the next generation in years, while genetic adaptations required 25,000 years to spread population-wide. How generalist biology that performs adequately in many places proved more valuable than perfect adaptation to one place. How teaching systems accelerated learning 3 to 5 times faster than observation alone. How language enabled transmitting complex knowledge that watching behavior could never convey. How technology created artificial adaptations, clothing substituting for fur, fire substituting for internal heat, tools extending capabilities in every direction. And how these factors work together, not adding but multiplying, creating flexibility no specialist species could match. If sleep finds you before the story ends, perfect. That's exactly why we're here. If these stories bring you rest, a subscription means you'll never run out of them. There's a Buy Me a Coffee link in the description if you'd like to help keep these stories coming, and a simple like helps someone else discover this quiet corner of the internet tonight when they need it most. Now settle in, get comfortable, and let's journey through the question of human adaptability, discovering through gentle exploration how our ancestors became the flexible species capable not of perfection in any single environment, but of adequate success in virtually every environment, achieving through remarkable mental and cultural capacities what no amount of biological specialization alone could provide. The world holds so many different places. Ice sheets spreading white to every horizon. Forests dense with green pressing close on all sides. Deserts where sand stretches hot under relentless sun. Mountains rising so high that breathing becomes difficult. Air thin and cold. Coasts where waves roll endlessly against rock and sand. Grasslands open and vast. Wind moving through endless grasses. Every environment different. Every place demanding different strategies for survival. Yet Homo sapiens live in all of them. Small groups scattered across landscapes that seem to have nothing in common. The same species, the same basic body, the same fundamental needs, but finding ways to survive in conditions so different that what works in one place would kill you in another. A person dressed for Arctic cold would die of heat exhaustion in hours if placed in desert sun. Someone adapted to breathing thin mountain air at 16,000 feet altitude would find no advantage in that adaptation at sea level. Food abundant in coastal regions simply doesn't exist hundreds of miles inland. Yet Homo sapiens groups establish themselves successfully in every one of these environments, not through having different bodies evolved separately for each place, but through something else entirely. The geographic range exceeds that of any other large mammal, from climates averaging 60 degrees below zero to climates regularly exceeding 130 degrees Fahrenheit. From sea level to elevations above 16,000 feet, where permanent human settlements exist, despite air containing 40% less oxygen than at coast. From regions receiving 200 inches of rain annually to regions where years can pass between rainfall events. Other animals specialize. The polar bear lives only in Arctic regions, superbly adapted with white fur for camouflage against ice and snow, with partially webbed paws for swimming through frigid water, with thick layers of fat, providing insulation against temperatures that can drop to 60 degrees below zero. Everything about the polar bear's body designed for one specific environment. That specialization creates excellence in Arctic conditions, but also creates limitation. The polar bear cannot live anywhere else. Place a polar bear in a temperate forest or tropical savanna, and it would struggle and likely die, not from lack of intelligence, but because its body is optimized for conditions that no longer exist around it. Its white fur becomes a disadvantage when hiding requires blending with brown and green backgrounds. Its thick, insulating fat becomes dangerous when external temperatures rise above freezing for extended periods. Its specialized hunting techniques for catching seals through breathing holes in ice become useless when no ice exists. The same pattern repeats across countless species. Camels thrive in desert conditions with humps storing fat reserves, with wide padded feet that don't sink into sand, with the ability to tolerate dramatic temperature swings and to go days without water. But camels exist only in arid environments. Mountain goats climb impossible slopes with hooves designed to grip tiny ledges, with bodies built for agility on steep terrain. But mountain goats struggle on flat ground. Deep sea fish live under crushing pressure in eternal darkness, with specialized organs that would fail if brought to the surface. Arctic foxes, desert lizards, rainforest monkeys. Each species shows excellence in specific conditions and severe limitations when those conditions change. Specialists outperform generalists in their optimized environments, but they cannot adjust when environments shift or when migration forces encounter with unfamiliar territories. Homo sapiens break this pattern completely. Groups live successfully in Arctic conditions, hunting across ice, building shelters from snow, wearing heavy furred clothing, existing in landscapes frozen 8 months each year. Other groups live in tropical rainforests where temperature and humidity stay high constantly, where the environment provides completely different resources, where staying warm becomes irrelevant, but staying cool becomes essential. Still other groups establish themselves in high mountain valleys, where altitude creates challenges no lowland environment presents, where thin air contains less oxygen with every breath. And others in deserts, where water scarcity becomes the dominant challenge, where daytime heat and nighttime cold create temperature swings of 50 degrees or more. The bodies don't differ dramatically between these populations. The same basic anatomy, the same organ systems, no specialized fur appearing in Arctic populations, no humps appearing in desert populations, no dramatic changes beyond minor variations. So if bodies don't change dramatically, what enables survival in such different places? The answer lies not in what bodies can do, but in what minds can do, and in how information moves between minds across time and space. The flexibility exists not in anatomy, evolved slowly over thousands of generations, but in behavior and knowledge that can change rapidly within lifetimes rather than across evolutionary epochs. A Homo sapiens group encountering a completely new environment can develop effective survival strategies within just 2 to 3 generations, roughly 50 to 75 years, through processes involving no genetic change whatsoever, but relying entirely on behavioral flexibility, observational learning, experimentation with new techniques, and social transmission of discovered solutions. A specialist species like the polar bear would face extinction if forced to transition to different environment because its adaptations are encoded genetically and cannot change within timescales shorter than thousands of generations. This demonstrates that Homo sapiens achieves adaptability not through superior physical specialization for any particular environment, but rather through cognitive and cultural mechanisms that allow rapid behavioral adjustment without waiting for biological evolution. Understanding human adaptability requires understanding how these mechanisms work, how minds substitute for specialized bodies, how learning replaces genetic programming, how culture transmits solutions faster than genes could spread them, and how cooperation pools knowledge beyond what any individual could discover alone. The wind across the ice carries a cold that penetrates layers of hide and fur. A group moves through this landscape, bundled against temperatures that would kill exposed skin within minutes. They know how to survive here through knowledge accumulated across generations, passed from parents to children through demonstration and instruction and practice. But their ancestors, perhaps only 10 generations back, lived in temperate woodlands where ice never formed, where winter meant cool dampness rather than lethal freezing, where different plants grew and different animals moved through different terrain. Those ancestors possessed the same bodies, the same genes, the same fundamental biology as the people now crossing ice sheets. Yet they lived successfully in completely different conditions, requiring completely different survival strategies. No genetic evolution occurred between those woodland ancestors and these Arctic descendants. The DNA remains essentially unchanged across 10 generations, far too brief for natural selection to create new biological adaptations. Yet the behavior changed dramatically. The woodland ancestors knew which temperate plants provided food and how to process them, knew how to hunt deer and small game in forested terrain, knew how to build shelters from wood and bark abundant in their environment. The Arctic descendants know which Arctic plants and lichens provide nutrition during brief summer, know how to hunt seals and caribou across open ice and tundra, know how to build shelters from snow and ice and transported materials. The knowledge changed completely while the bodies stayed the same. This represents behavioral adaptation without genetic evolution, the foundation of human flexibility. The capacity for such behavioral change rests on cognitive flexibility, the ability of minds to try different approaches when existing approaches stop working, to recognize when environmental conditions demand different strategies, and to generate and test new solutions to survival challenges. Many species show relatively fixed behavioral patterns driven by instinct that evolved to work in specific conditions. When those conditions persist, the fixed behaviors succeed. When conditions change beyond certain ranges, the behaviors fail, but continue anyway because the animal cannot easily modify instinctive responses. A bird species that evolved migration timing triggered by day-length changes might continue migrating at the evolved time even when climate change shifts the optimal migration timing because their trigger mechanism lacks flexibility to adjust to new patterns. Homo sapiens show much greater behavioral flexibility. If a hunting technique that worked reliably for years suddenly stops producing food, human hunters recognize the failure and deliberately try different approaches rather than repeating the unsuccessful strategy indefinitely. If familiar plant foods become scarce, gatherers experiment with alternative plants, testing carefully for edibility, observing what animals eat for clues about potential food sources. If traditional shelter designs prove inadequate under changed weather patterns, builders modify designs, trying different materials or configurations or orientations until they develop approaches that work under new conditions. This willingness and ability to abandon failing strategies and experiment with alternatives requires cognitive capacity to recognize failure, to generate potential alternatives, to evaluate which alternatives seem worth trying, and to implement new approaches despite uncertainty and risk. The brain functions as an adaptation organ, generating behavioral variation that can be tested against environmental conditions, keeping successful variants and discarding unsuccessful ones. This creates an evolutionary process operating within individual lifetimes through learning rather than across many generations through genetic change. The speed difference becomes crucial for survival when environments change rapidly. Genetic evolution through natural selection typically requires 1,000 to 2,000 generations for a beneficial trait to spread from rare mutation to population-wide prevalence. For species with generation times around 25 years, this means 25,000 to 50,000 years for genetic adaptation to new conditions. Behavioral adaptation through learning can accomplish functional adjustment in years or decades rather than millennia, a 1,000-fold speed advantage that explains how Homo sapiens expanded into diverse environments within timescales impossibly short for genetic adaptation. Mental modeling and causal reasoning enhance this behavioral flexibility by allowing simulation of potential consequences before acting. Homo sapiens can think through what might happen if they try particular approaches, using understanding of cause and effect relationships to predict outcomes. If considering building a shelter in a new location, people can mentally simulate whether that location would flood during rain, whether wind would penetrate the structure, whether the opening should face particular directions for light or warmth. This mental simulation reduces need for pure trial and error, where every possibility must be attempted physically to determine results. Many poor options can be rejected through mental analysis, with physical effort directed toward approaches that mental modeling suggests might succeed. The ability to think about environmental relationships, to understand that water flows downhill and collects in low areas, that wind typically comes from particular directions, that sun position changes through seasons, allows anticipation and planning that improves adaptation. Success rates dramatically. A person understanding these relationships can predict that a shelter built in a depression might flood, that an opening facing prevailing winds will be cold, that placing the shelter where morning sun reaches it provides early warmth. This predictive capacity emerges from observing patterns across many experiences and building mental models of how the world works, then applying those models to new situations. The models need not be scientifically accurate in modern terms to be useful. They must simply capture enough regularity about how things behave to enable predictions better than random guessing. Memory capacity supports behavioral flexibility by storing detailed environmental knowledge accumulated over years of experience. The landscape changes through seasons. What grows or moves through an area in summer differs from winter. Water sources reliable in spring might disappear by autumn. Understanding these patterns requires remembering past observations across months and years, building mental maps of territories and mental calendars of seasonal variations. Human memory handles this complexity successfully, storing not just simple facts, but detailed spatial and temporal information about where resources exist, when they become available, how to recognize conditions indicating their presence. A hunter's knowledge might include hundreds of observations about how different animals react to weather, time of day, season, terrain. A gatherer's knowledge might include recognition of dozens of plant species, understanding which parts are edible when, awareness of preparation methods, memory of which locations produce which plants in which seasons. This accumulated knowledge provides environmental expertise enabling survival, and its existence in flexible memory rather than fixed genetic programming allows adjustment as environments change or as people move into new territories requiring different knowledge. When the environment shifts, the old knowledge becomes less useful, but the learning mechanisms remain functional, allowing acquisition of new knowledge appropriate for new conditions. When people migrate into unfamiliar territories, they can observe the new environment intensively, experiment carefully with its resources, and gradually build knowledge bases about the new region similar in complexity to knowledge they possessed about their original territories. The brain's flexibility in what it can learn, rather than being restricted to narrow domains by genetic programming, enables this transfer of learning capacity across different environments and challenges. A child watches an adult working with stone, striking one piece against another, removing flakes systematically until a sharp edge emerges. The child sees the angle of strikes, the force used, which parts of the stone get removed in what sequence, how to hold the materials, when to rotate the piece to work different areas. Later, when given stone to work with, the child attempts to replicate what was observed. The first attempts produce crude results, but with practice and more watching, the technique gradually improves. The child learns a skill that took the adult years to master, learning in months what might have taken years to discover through pure trial and error without the benefit of watching skilled performance. This observational learning provides a fundamental mechanism for knowledge transmission across individuals and generations. Young humans spend enormous time watching what older, more experienced individuals do. They observe how adults process foods, construct tools, build shelters, track animals, interact with environmental features. Through observation, they acquire skills without needing to discover everything themselves through potentially dangerous personal experimentation. A child watching an adult carefully prepare a particular plant by removing certain parts, soaking the remainder in water, then cooking it, learns the preparation procedure without needing to discover personally that eating the plant raw causes illness. The observer benefits from the teacher's knowledge, gained perhaps through years of experience or passed from previous generations, without paying the cost in time and risk that acquiring knowledge through pure trial and error would require. The effectiveness of observational learning appears early in human development. Infants only months old distinguish successful from unsuccessful actions when watching others and show preference for watching successful actions, suggesting they extract meaningful information from observed behavior before they can understand verbal explanations. Toddlers readily imitate adult actions even when those actions serve no obvious immediate purpose, suggesting a general tendency to copy observed behaviors as a learning strategy. By age 3 or 4, children learn complex multi-step procedures through observation, remembering sequences of actions they watched adults perform and reproducing those sequences when given opportunity, sometimes with remarkable accuracy, considering they may have seen the procedure only once or twice. This early emerging observational learning capacity means human children begin acquiring cultural knowledge before they can speak full sentences, building survival-relevant skills throughout childhood through constant observation of competent adults demonstrating techniques through their daily activities. For skills involving visible motor actions, observation works extremely well. Watching someone weave plant fibers into cordage reveals the twisting motion, the tension maintained, how new fibers get added as old ones end, the pattern emerging from repeated motions. A learner watching can see these details and attempt replication with practice, gradually improving technique toward the skilled performer's level. For tasks involving visible environmental manipulation, like constructing a shelter or processing a plant, observation provides rich information about what steps occur, what materials get used where, what the final result should look like. The key advantage lies in bypassing much of the trial and error phase. Instead of trying hundreds of random approaches to discover what works, the learner starts with a known working approach visible through observation and focuses effort on refining execution rather than discovering basic techniques. However, observational learning has inherent limitations for certain types of knowledge. When important information is not directly visible in behavior, observers may struggle to extract it through watching alone. Consider a skilled hunter tracking animals. The visible behavior involves walking while looking at ground, occasionally stopping to examine something closely, perhaps altering direction. But much of the expert knowledge remains invisible. What subtle signs they're reading in footprints, broken vegetation, scent traces, how they're interpreting those signs to infer the animal's size and direction, and how long since it passed. An observer watching the tracker might see where they go and what they look at, but extracting the underlying reasoning from visible behavior alone becomes difficult. The observer learns something through repeated watching and through trying to track themselves, but the learning process remains incomplete without additional information. This limitation creates the value of active teaching that supplements observational learning with deliberate information transmission. Teaching combines demonstration with verbal explanation, focused attention to key details, and structured practice with feedback, dramatically accelerating skill acquisition beyond what observation alone achieves. Research comparing learning rates suggests active teaching produces skill acquisition roughly 3 to 5 times faster than pure observational learning without instruction, and perhaps 10 to 15 times faster than solo trial and error learning with no social input. The acceleration compounds across the many skills any individual must learn, dramatically reducing time required to reach functional competence. A child receiving active teaching in hunting, gathering, tool making, shelter construction might reach adult competence in 12 to 15 years, whereas attempting to acquire the same knowledge through pure trial and error might require 30 years or more if it succeeded at all. The neural mechanisms enabling imitation involve specialized brain systems that activate both when performing an action and when observing another person perform the same action. These systems allow the observer's brain to internally simulate the observed action, creating a mental representation of the motor sequence that can then guide the observer's own attempts to perform the action. This neural mirroring facilitates learning by creating direct mapping between observed behavior and the motor programs needed to reproduce that behavior. The sophistication of human imitative abilities exceeds that seen in other primates, allowing faithful copying of complex action sequences, including subtle details of technique that make the difference between effective and ineffective performance. This enhanced imitation capacity forms part of the cognitive toolkit supporting human cultural learning and transmission. Observational learning operates not just from children watching adults, but also horizontally among peers and across groups. When someone discovers a better technique, that innovation can spread to others in the group within days or weeks as people observe it being used successfully and attempt it themselves. If one hunter discovers that a particular plant attracts game animals and uses this for more successful hunting, other hunters observing the technique can adopt it immediately rather than waiting for the next generation to be taught. Information flowing horizontally through adult social networks means innovations can impact the entire current generation, not just future generations, accelerating adaptation because the group benefits from new knowledge within months rather than decades. An adult sits with a young learner, working carefully with strips of plant material, demonstrating how to weave them into sturdy cordage. The motions proceed slowly, deliberately, more slowly than the adult would work when making cordage for actual use. The adult pauses frequently, pointing out details, explaining why the twist goes in particular direction, showing what happens if tension becomes too loose or too tight, demonstrating how to add new material when the current strip ends. When the learner tries, the adult watches closely, immediately noticing when the twist reverses incorrectly, gently correcting the error, guiding the learner's hands to feel the right motion. This interaction represents active teaching, distinct from mere observation, where an experienced individual deliberately structures learning to accelerate the novice's skill acquisition. Teaching carries costs to the teacher. Time spent instructing is time not spent on personal survival activities like food acquisition or shelter maintenance. Teaching requires patience when learners struggle or make errors repeatedly, and it provides no immediate survival benefit since the learner cannot yet contribute effectively. Yet human adults regularly engage in extensive teaching behavior, investing substantial time and effort in helping children and inexperienced adults acquire skills. This teaching motivation evolved because in social groups, individual success depends partly on group success. If the group thrives, individuals benefit through cooperation, defense, shared resources, social support. If the group struggles because the younger generation never acquires necessary skills, everyone suffers, including potential teachers who chose not to teach. Additionally, kinship relationships mean that teaching one's own children and close relatives aids survival of shared genes, even when teaching doesn't benefit the teacher directly. The cognitive capacity for teaching requires sophisticated mental abilities beyond those needed for personal learning. Effective teachers maintain mental models of what the learner knows and doesn't know, recognizing knowledge gaps needing address. They adjust instruction to the learner's current level, neither providing information too advanced to understand nor wasting time on what the learner already grasps. They monitor the learner's progress and understanding, recognizing when confusion occurs, even if not verbally expressed, and adapting teaching strategy accordingly. They anticipate common errors or misconceptions and address them proactively. They sequence information presentation logically, teaching prerequisite knowledge before advanced applications. These teaching skills reflect sophisticated social cognition, including theory of mind capabilities that allow modeling others' mental states and knowledge levels. When an experienced tracker actively teaches a novice, They make invisible reasoning visible through explaining what signs they're reading and what those signs mean, pointing out subtle features the novice's untrained eye might miss, describing animal behavior patterns that inform interpretation, providing practice opportunities where the novice attempts tracking while the teacher observes and corrects errors in real time. This active instruction transmits knowledge difficult or impossible to acquire through observation alone. The teacher might explain that tracks appearing crisp and deep indicate the animal passed recently, perhaps within the hour, while tracks with softened edges indicate passage many hours earlier, maybe yesterday. They might point out how vegetation bent in particular direction shows the animal's travel path, or how specific scents lingering in the air provide information about the animal's recent presence. Without verbal explanation making these observations explicit, a learner might eventually notice some patterns through extensive experience, but the learning would proceed far more slowly, and many subtle indicators might never become apparent. The teaching process often involves deliberate simplification and progressive difficulty increase, starting with basic concepts and gradually building toward more complex applications as the learner's competence grows. When teaching tool making, an instructor might begin with simple flaking of stone to create any sharp edge, then progress to controlled flaking that shapes edges more precisely, then advance to techniques for thinning pieces and creating specific tool forms. Then eventually teach specialized techniques for difficult materials or complex tool types. This progressive scaffolding allows the learner to build skills systematically rather than being overwhelmed by attempting advanced techniques before mastering basics. The teacher's role includes assessing when the learner is ready to progress to next difficulty level, providing sufficient practice at each level to establish competence before advancing. Active teaching includes error correction, where the teacher identifies mistakes in the learner's performance and provides feedback about what went wrong and how to improve. This feedback dramatically accelerates learning because it prevents the learner from practicing errors that might become habits, and it provides explicit information about the difference between current performance and target performance. When a learner attempting to start fire by friction moves the drill too slowly or at wrong angle or without adequate pressure, the teacher can immediately point out the error and demonstrate the correct technique, allowing the learner to adjust their approach on the next attempt. Without such feedback, the learner might practice ineffective technique repeatedly, not understanding why success eludes them, potentially concluding the task is impossible when actually their technique simply needs adjustment. The teacher's intervention short-circuits this frustrating process by providing the specific information needed for correction. Verbal explanation during teaching adds a dimension impossible to convey through demonstration alone. The teacher can explain the reasoning behind techniques, the principles that might extend to other situations, the circumstances that require modifications of standard approaches. Explaining that fire needs three elements working together: fuel that burns, heat sufficient to start combustion, and oxygen from airflow, provides a conceptual framework that helps the learner understand why certain conditions succeed while others fail. This conceptual understanding enables the learner to troubleshoot problems independently and to adapt techniques to varying conditions, rather than simply memorizing a fixed procedure that only works under specific circumstances. The shift from procedure following to principle understanding represents a qualitative advance in competence that teaching through explanation facilitates more effectively than observation alone could achieve. The teaching relationship creates social bonds between teacher and learner that extend beyond the immediate instructional context. These bonds support ongoing learning because the learner feels comfortable asking questions, admitting confusion, requesting additional help when needed. The teacher invests in the learner's success and feels satisfaction when the learner progresses. This social-emotional dimension of teaching helps sustain the investment of time and effort required for transmitting complex skills, and it creates a cultural pattern where knowledge transmission is valued and expected. Societies that develop strong teaching traditions, where adults routinely and systematically teach children necessary skills with patience and care, produce generations that reach competence more reliably and rapidly than societies where learning occurs primarily through observation without active instruction. The teaching culture itself becomes an adaptive advantage, a form of social organization that enhances knowledge transmission effectiveness. Imagine two populations facing environmental challenges. The first population relies on genetic evolution to adapt. A beneficial mutation occurs that improves survival under new conditions. That mutation exists initially in just one individual. For it to spread through the population, individuals carrying the mutation must have higher reproductive success than those without it, and they must pass it to their offspring. And those offspring must also have higher success, and this differential must continue across many generations. Population genetics models indicate this process typically requires 1,000 to 2,000 generations minimum, even for strongly beneficial mutations. For species with generation times around 25 years, this means 25,000 to 50,000 years for genetic adaptation to spread population-wide. Now imagine a second population capable of cultural evolution. Someone invents a better hunting technique that increases success rates. That invented technique can spread to other hunters in the group within days, as others observe it being used successfully and ask to learn it. Within weeks or months, most competent hunters in the group might adopt the improved technique. Within 20 to 25 years, as the next generation of children grows old enough to learn hunting skills, they would learn the improved technique as standard practice, perhaps not even knowing different methods were used previously. The innovation has become cultural knowledge passed to the next generation, solidly established in roughly one generation. When those children grow up and teach their own children, the technique passes again, locked in through cultural transmission unless something better gets invented. Total time from innovation to secure establishment. Perhaps 50 years, 2 generations, roughly 1/1000th the time genetic adaptation would require for equivalent improvement. This 1,000-fold speed advantage in adaptation rate through cultural versus genetic transmission explains much of human geographic range and adaptability. When Homo sapiens groups encountered new environments during their expansion across Earth, they needed to adapt to dramatically different conditions, from tropical heat to Arctic cold, from dense forests to open grasslands to mountain heights to coastal zones. No specialist species could evolve the necessary genetic adaptations for such diverse environments in the timescales involved. The polar bear's adaptations to Arctic hunting required millions of years of evolution. The camel's desert adaptations similarly developed over vast timescales. But Homo sapiens moved from tropical and temperate regions into Arctic environments, into deserts, into high mountains, into countless different ecological zones within timescales measured in thousands of years rather than millions, because the necessary adaptations occurred primarily through cultural and behavioral change rather than genetic change. When encountering cold climates for the first time, people didn't wait for genes for thicker body hair or subcutaneous fat layers to evolve over tens of thousands of generations. They invented clothing and learned how to make it from available materials, discovering through experimentation which animal hides provided best insulation, how to cure and prepare hides to remain flexible, how to sew pieces together to cover the body effectively, how to design garments that trapped warm air while allowing freedom of movement. They developed shelter-building techniques appropriate for cold conditions, learning how to construct walls that blocked wind, how to create roofs that shed snow, how to insulate with materials available in cold environments, how to arrange living spaces to maximize warmth from fire and body heat. They learned cold weather food acquisition strategies, discovering which animals remained available during winter, where to find them, how to hunt across ice and snow, how to preserve meat for times when hunting success declined. These cultural adaptations could be invented, tested, refined, and transmitted within years or decades, enabling successful colonization of cold regions within centuries, rather than requiring millions of years for genetic cold weather adaptations to evolve. The same pattern repeated for every new environment encountered. Desert survival didn't require evolution of camel-like water storage or specialized kidney function. Instead, people developed cultural knowledge about where water sources existed, even in arid landscapes, when to travel to minimize water loss through exertion in heat, how to store and transport water in containers, which plants provided moisture, how to recognize signs of water presence from animal behavior and vegetation patterns. High-altitude adaptation didn't require millions of years for genetic changes improving oxygen utilization. Instead, groups learned which mountain valleys provided adequate resources, how to adjust physical exertion to reduced oxygen availability, what techniques worked for hunting mountain animals, when seasonal patterns made high valleys accessible or forced retreat to lower elevations. Cultural solutions developed rapidly enough that populations survived and thrived before genetic adaptations could possibly emerge. The speed advantage of cultural adaptation becomes even more apparent when considering that environments themselves change over time through climate shifts, seasonal variations, resource fluctuations, and migrations of plant and animal populations. A species relying purely on genetic adaptation might evolve perfectly for one set of conditions, only to find those conditions have changed by the time the genetic adaptation spreads through the population, requiring a new round of genetic evolution that might again lag behind environmental change. Cultural adaptation can track environmental changes more closely because the adaptation timescale of years or decades matches reasonably well with the timescale of many environmental variations. If climate shifts make traditional food sources less available, a group can experiment with alternative foods and develop new procurement strategies within 1 or 2 generations, rather than waiting thousands of generations for genetic dietary adaptations. If weather patterns change, requiring different shelter designs, builders can modify techniques within years rather than waiting for genetic evolution of different physiological temperature regulation. The cultural system's responsiveness to environmental change provides adaptive tracking that genetic evolution cannot match. Cultural transmission operates through the teaching and learning mechanisms that allow solutions discovered by any individual to spread throughout the group and pass to subsequent generations through social learning rather than genetic inheritance. When someone invents an improved tool design, others can adopt that design immediately upon seeing it demonstrated, and all children born subsequently learn the improved design as standard, with the innovation spreading horizontally to the current generation and vertically to future generations simultaneously. This dual transmission creates rapid establishment. By contrast, genetic transmission flows only vertically from parents to offspring, never horizontally between unrelated adults, and the spread requires differential reproduction across many generations. The cultural system's ability to transmit innovations both horizontally and vertically accelerates adaptation dramatically compared to purely genetic systems that transmit only vertically and only through reproduction across generation boundaries. The human body, examined against specialist species, shows relatively generalist design across most systems. This generalist pattern means performing adequately across many different environmental conditions rather than performing optimally in any single condition. The strategy proves more valuable for adaptability than the optimal in one approach that specialists employ. Understanding this requires examining what generalist biology provides and what limitations it accepts in exchange for flexibility. The digestive system exemplifies this design. Homo sapiens are omnivores, capable of extracting nutrition from both plant and animal sources across a wide range of food types. The digestive tract includes teeth suitable for grinding plant materials and tearing meat, stomach acid strong enough to break down animal proteins, but not so extreme as to prevent plant digestion, intestines of intermediate length that process diverse foods reasonably well, though not as efficiently as specialist digesters. This omnivore system means humans can survive on diets consisting primarily of meat, as some Arctic populations do when plant foods are scarce for much of the year, or primarily of plant foods, as some tropical populations do when large game animals are difficult to hunt, or any mixture in between, depending on what the local environment provides. The flexibility comes with cost. Humans don't digest cellulose as effectively as dedicated herbivores like cattle with their multiple stomach chambers and specialized gut bacteria. Humans don't process raw meat quite as efficiently as dedicated carnivores like lions with their shorter digestive tracts and stronger stomach acids optimized for pure meat diets. But this moderate efficiency across many food types proves more useful than optimal efficiency for one food type because it allows dietary adjustment when environments change or when moving into new regions with different available foods. When Arctic populations eat primarily meat and fat, their digestive systems function adequately. When tropical populations eat primarily fruits and tubers with occasional meat, the same digestive design also functions adequately. The same system serves both extremes and everything in between. Dentition supports this flexibility. Human teeth include incisors for cutting, canines somewhat larger than typical herbivore canines, but much smaller than carnivore canines, and molars suitable for grinding. This dental arrangement works reasonably well for many different foods without being perfectly designed for any particular food type. Contrast with specialist dentition, like the ever-growing incisors of rodents optimized for gnawing tough plant materials, or the massive canines and scissor-like carnassial teeth of big cats optimized for killing prey and shearing meat from bone, or the complex grinding molars of dedicated herbivores designed to process enormous quantities of tough plant fiber. Human teeth do none of these things optimally, but they do all adequately, which creates flexibility to shift diet based on what foods and environment offers, rather than requiring specific food types that genetics demand. Locomotion shows similar generalist design. Homo sapiens bipedalism works across many different terrain types without being optimized for any single terrain. Humans walk and run reasonably efficiently on flat ground, can navigate rocky or uneven terrain with care, can climb when necessary, though not as well as dedicated climbing specialists, can wade or swim, though not as efficiently as aquatic specialists. The upright posture and freed hands create advantages for tool carrying and manipulation. But the locomotion system itself shows flexibility rather than specialization. Contrast with the cheetah's body optimized for high-speed pursuit running on open ground, but poor at climbing or swimming, or the mountain goat's hooves and body proportions optimized for steep rocky terrain, but awkward on flat ground, or the gibbon's long arms optimized for brachiating through forest canopy, but inefficient for ground travel. Human locomotion doesn't excel at any of these, but functions adequately for all, allowing Homo sapiens to inhabit environments ranging from open plains to rocky mountains to forests without requiring different body structures for each terrain type. Thermoregulation similarly shows generalist capacity with cultural enhancement. The human body maintains core temperature across a moderate range of environmental temperatures through combination of metabolic heat generation, sweating for evaporative cooling when hot, and shivering for additional heat when cold. But native temperature tolerance without technological assistance is fairly narrow, probably around 15 to 30 degrees Celsius, for comfortable long-term survival with minimal clothing. This represents much less thermal tolerance than specialists achieve. Polar bears maintain body temperature comfortably in conditions that would kill unprotected humans within hours. Desert animals like camels tolerate temperature swings and heat levels that would cause human heat stroke. But human bodies possess enough baseline temperature regulation that with cultural and technological assistance, they extend their effective tolerance enormously. Clothing provides artificial insulation in cold, effectively substituting for the thick fur that cold-adapted specialists evolved over millions of years, but doing so through technology that can be invented and improved within generations. Fire provides artificial heat sources that warm living spaces beyond what body heat alone could achieve. Shelter design controls thermal environments, trapping heat when cold outside or promoting air circulation when hot. Behavioral adaptations like timing activity to cooler or warmer parts of day, seeking shade or sun deliberately, adjusting water consumption and exertion levels all extend thermal tolerance further. The result is effective survival across temperature ranges from Arctic cold to desert heat, achieved not through specialized anatomy evolved for temperature extremes, but through generalist baseline physiology that functions adequately across moderate conditions, plus cultural and technological enhancements that extend capability far beyond what biology alone provides. Water requirements show similar patterns. Human kidneys can concentrate urine to conserve water reasonably well, but not as extremely as desert specialists like camels or kangaroo rats that produce extremely concentrated urine and can survive on moisture from food alone. Humans can tolerate some dehydration, but not the extreme dehydration that desert specialists handle routinely. But humans supplement their moderate physiological capacity through behavior and technology, seeking and storing water sources, scheduling activity to reduce water loss, using containers to transport water from sources to living areas, developing knowledge of where water exists seasonally, and how to recognize signs of water presence, sometimes digging to reach groundwater or collecting dew or rain. These cultural and technological solutions extend water-scarce tolerance beyond what physiology alone would allow, enabling successful desert survival without requiring genetic evolution of extreme water conservation physiology. Sensory systems show generalist design. Human vision functions across bright daylight and dim conditions with reasonable color discrimination and pattern recognition, but without the extreme low-light capabilities of nocturnal specialists or the extreme distance vision of raptors. Human hearing covers a moderate frequency range without the echolocation of bats or the infrasound detection of elephants. Human smell is moderate, more sensitive than some mammals, but far less than tracking specialists like bloodhounds. These moderate sensory capabilities work adequately across many environments without excelling in any particular sensory domain. Cultural knowledge and technology compensate for sensory limitations. Understanding animal behavior patterns helps locate game without needing to detect scent from miles away. Understanding seasonal patterns helps predict where resources will be. Social information sharing means the group's collective sensory observations exceed any individual's sensory capacity. The generalist biological strategy carries an important implication. Homo sapiens never outperform specialists in the specialist's optimized environment when comparing pure biological capabilities. A human cannot outrun a cheetah, cannot outswim a seal, cannot outclimb a monkey, cannot survive cold as well as a polar bear without cultural assistance, cannot digest plant fiber as efficiently as a cow, cannot detect scent trails as effectively as a wolf. In direct physical competition using only biological capabilities, the specialist wins every time. But this limitation doesn't matter for adaptability because humans rarely rely solely on biological capabilities. The relevant comparison is not human biology versus specialist biology, but rather human biology plus culture and technology versus specialist biology. And in that comparison, human adaptability exceeds specialist capabilities dramatically. Fire burns in the center of the shelter, warmth spreading outward, pushing back the cold that presses against the walls from outside, where temperature has dropped far below freezing. The people gathered around the fire stay comfortable in conditions that would kill them within hours without this artificial heat source. Their bodies did not evolve the thick fur of Arctic wolves or the layers of insulating fat of polar bears. Instead, they invented fire, controlled it, maintained it, created through technology what genetic evolution never provided. The flames represent something fundamental about human adaptability, the capacity to create artificial adaptations through technology that substitute for biological specializations, and to create them within timescales measured in generations rather than millions of years. Clothing provides perhaps the most essential technological adaptation for cold environments. Animal hides carefully prepared and sewn together create artificial insulation that traps warm air close to the body, functioning analogously to the fur that cold-adapted species evolved genetically. But where genetic evolution of protective fur required countless generations of natural selection favoring individuals with thicker, more insulating hair, cultural evolution of clothing occurred within time frames of years or decades. Someone discovered that wrapping animal skins around the body provided warmth. Someone figured out how to clean and prepare hides to remain flexible rather than becoming stiff. Someone invented the concept of piercing holes and threading strips through them to join pieces together. Someone designed garments that covered vulnerable areas while allowing freedom of movement. Each of these innovations built on previous knowledge, with the cumulative result being effective cold weather clothing that enabled human survival in Arctic conditions without requiring any genetic changes to the human body. The same naked human that would die of exposure in Arctic cold within hours survives successfully when wearing appropriately designed clothing, demonstrating that the adaptation exists in the technology rather than the biology. The clothing adaptation shows remarkable flexibility compared to biological adaptations. Genetic fur cannot be removed when conditions warm up. The polar bear carries its thick coat year-round, which works well in persistently cold Arctic environment, but would become a severe liability in temperate or tropical climates where the inability to shed insulation would cause dangerous overheating. Human clothing can be removed when not needed, put on when conditions demand it, adjusted in layers to match varying conditions, modified in design when moving between different climates or seasons. Someone moving from cold environment to warm environment simply removes heavy clothing, functioning effectively in the new conditions without needing to wait for genetic evolution to remove biological cold adaptations that are no longer beneficial. This adjustability within individual lifetimes provides enormous advantage over fixed biological adaptations that persist across thousands of generations, whether currently useful or not. Shelter construction creates another form of artificial adaptation, building controlled environments that buffer inhabitants from external conditions. A well-designed shelter blocks wind that would otherwise strip body heat through convection, keeps out precipitation that would cause dangerous heat loss through evaporation, traps heat generated by fire and bodies to maintain comfortable interior temperature even when exterior temperature drops to lethal levels. The shelter effectively creates a microclimate more favorable than the surrounding environment, allowing humans to survive in conditions their naked bodies could not tolerate. Different environments demand different shelter designs, and the flexibility of cultural solutions allows appropriate designs to develop for each context. Arctic shelters might use snow for insulation, be built partially underground to escape wind, have small openings to minimize heat loss. Tropical shelters might use lightweight materials, be elevated for air circulation, have large openings to promote cooling, protect from rain and sun, but not focus on heat retention. The same people could learn to build either design depending on their environment, switching construction strategies as readily as switching clothing types, achieving through technological flexibility what biological adaptation could only accomplish through possessing different body structures for different climates. Tools extend human physical capabilities into domains where biological evolution might require millions of years to develop equivalent specialized anatomy. Sharp stone edges cut more effectively than human fingernails ever could, substituting for the claws that predators evolved for tearing flesh. Spears thrown or thrust extend striking range beyond what arms alone provide, compensating for lack of the long necks or powerful jaws that allow other predators to attack from distance or with tremendous force. Containers made from bark or hide or woven plant fibers carry water or gathered foods more efficiently than human hands alone could manage, substituting for the cheek pouches or specialized stomach compartments that some animals evolved for food transport and storage. Needles made from bone or thorn allow precise piercing and threading impossible with fingers alone, enabling the tailoring that makes effective clothing possible. Each tool represents a functional capability that humans lack biologically, but create technologically, achieving through invention what evolution might eventually create through genetic change, but doing so within time frames of human lifetimes rather than evolutionary epochs. The pace of technological innovation dramatically exceeds the pace of biological evolution. Archaeological evidence shows human tool types changing noticeably every 20,000 to 50,000 years during most of the Paleolithic period, with innovation rates accelerating in later periods. This represents rapid change compared to biological evolution, where species anatomy remains relatively stable over hundreds of thousands of years. But even this represents slow technological change compared to what becomes possible once cultural transmission systems become highly effective. When innovation and transmission mechanisms work efficiently, New technologies can spread through populations within years or decades and can accumulate improvements across generations, creating exponential growth in technological sophistication. The same cognitive and cultural mechanisms that allow invention of stone-cutting tools also allow invention of fire-starting tools, clothing, shelters, containers, cordage, and countless other technologies, each extending human capabilities into new domains. Technology creates not just individual tools, but integrated technological systems where multiple innovations work together synergistically. Cold weather survival requires not just clothing alone, but rather the combination of appropriate clothing, shelter design, fire making and fire management techniques, specialized tools for working stiff frozen materials, knowledge of cold weather food sources and preservation methods, and social organization that shares these various responsibilities across group members with different skills. The complete cold weather adaptation emerges from this technological and social system, rather than from any single innovation. This systemic nature of cultural adaptation contrasts with biological adaptation, where a genetic mutation typically affects one trait at a time. The ability to invent and integrate multiple complementary technologies simultaneously creates adaptive power exceeding what genetic evolution's more piecemeal approach can achieve within comparable time frames. The flexibility of technological adaptation also appears in how technologies can be modified for local conditions using locally available materials. The principle of sharp cutting edge remains constant, but the specific material used to create that edge varies by region. Where high-quality flaking stone exists, people develop stone tool technologies. Where suitable stone is rare but bone is available, bone tool traditions develop. Where plant materials dominate, wood and bamboo technologies emerge. The same functional need generates different specific technological solutions depending on environmental context, with each population developing technologies appropriate for their local resource base. This local adaptation of technology happens rapidly through experimentation and selection of what works well with available materials, much faster than biological evolution could produce regionally specific genetic adaptations. 3 people sit examining a plant none of them have encountered before. The region is new to the group, recently arrived after several years of travel from their traditional territory where different plants grew. This unfamiliar plant grows abundantly nearby, and knowing whether it provides food would significantly affect the group's survival prospects. One person recalls that a plant with similar leaf shape grew in the old territory and was edible. Another person notes that birds were seen eating the seeds, suggesting possible safety. A third person has knowledge about plant families and observes characteristics suggesting this plant might belong to a family that typically produces toxic compounds requiring special processing. Together, they pool their separate observations and knowledge domains, arriving at a decision to try the plant carefully, starting with small amounts, preparing it by the method used for the similar plant from their old territory, watching for any ill effects before consuming more. This collaborative problem-solving exemplifies how social cooperation multiplies adaptive capacity beyond what any individual could achieve alone. Each person brings different knowledge, different observations, different reasoning to the challenge. The first person's memory of the similar plant provides a starting hypothesis about edibility and possible processing methods. The second person's observation of birds eating it provides evidence about safety, though not conclusive since bird digestive systems sometimes tolerate compounds toxic to humans. The third person's broader knowledge about plant families adds important caution about potential toxins. No single individual possesses all this information, but the group collectively combines information from multiple sources to make a more informed decision than any lone person could reach. The principle extends across all survival domains. When tracking animals, different hunters notice different signs. One might spot subtle footprints another missed. One might recognize how vegetation disturbance indicates the animal's passing. One might detect scent traces. One might recall that this animal species tends to move toward water sources in afternoon. Pooling these separate observations creates a more complete picture of where the animal went and where it might be found than any single tracker's observations could provide. When building shelter, one person might have experience with structural stability, another with material properties, another with techniques for waterproofing, another with optimizing interior layout. Combining their knowledge produces better shelter design than any individual working alone would likely achieve, especially when facing unfamiliar conditions or materials. Division of labor within groups creates another advantage. While all adults typically possess general competence across essential survival skills, individuals often develop particular expertise in domains they practice frequently or have natural aptitude for. One person becomes especially skilled at tracking and hunting. Another develops expertise in plant knowledge and gathering. Another excels at tool making. Another becomes highly proficient at fire starting and fire management. When the group can rely on different individuals' specialized expertise, while those specialists still maintain adequate general skills as backup, the overall group capability exceeds what a collection of identical generalists could achieve. The tracker focuses attention on improving tracking skills, becoming more effective than if attention was distributed equally across all skill domains. The toolmaker refines techniques through concentrated practice, producing better quality tools than part-time toolmaking would generate. Each specialist contributes their domain of excellence, while the group as a whole maintains coverage across all necessary skills. This division of labor works only in social context where individuals cooperate and share. The tracker who spends whole days pursuing game must trust that others are gathering plant foods, maintaining fire, watching children, constructing shelters. The toolmaker who invests time in careful crafting must know others will share food during that investment period. The cooperation emerges from combination of kinship relationships where helping relatives aids shared genetic success, reciprocal relationships where helping others now creates expectations of receiving help later, and social norms that establish expectations about sharing and contribution to group welfare. These social mechanisms support the cooperative division of labor that allows specialized expertise to develop while maintaining group security through distributed skills. Information sharing increases collective knowledge beyond any individual's experience. A single person lives perhaps 50 to 70 years, experiences a limited set of environmental conditions, encounters a finite number of situations, makes a bounded set of observations. But a group of 30 to 50 people collectively accumulates much more experience. Some individuals have seen rare weather events that others missed. Some have encountered particular animals or plants in circumstances others haven't. Some have traveled through regions others never visited. When information flows between individuals through conversation and storytelling, the group develops collective environmental knowledge pooled from many lifetimes of observation, creating a knowledge base far larger than any individual memory could hold. An elder might remember the severe drought that occurred 40 years earlier, information crucial for the current generation if similar conditions return. A returning traveler might describe resources or conditions in distant territories, information valuable for future decisions about movement or trade. Multiple individuals' observations of the same phenomena from different perspectives can reveal patterns or regularities that single perspective might miss. Social learning networks extend beyond immediate kin groups to include interactions among different bands that meet periodically. Mobile groups occupying different territories might encounter each other seasonally at resource-rich locations or might deliberately travel to visit for social purposes. These intergroup meetings create opportunities for knowledge exchange across populations. If one group has developed an improved tool design or discovered a new food processing technique or learned about resources in their area, that information might spread to other groups within the network within years or decades, rather than remaining isolated to the originating population. This horizontal knowledge flow across social networks creates larger effective population sizes for cultural innovation than actual group sizes, because any discovery anywhere in the network can potentially benefit everyone connected to the network, not just the local group where innovation first occurred. The social dimension of adaptation also includes collective decision-making about group movements, resource use, responses to threats or opportunities. Important decisions affecting group survival, like whether to migrate to new territory or remain in current location, which direction to travel if moving, how to respond to encounters with other groups, often benefit from multiple perspectives and collective wisdom. Discussing options allows consideration of different viewpoints, identification of risks that some individuals recognized but others missed, combination of different knowledge domains relevant to the decision. While not all decisions require group consensus, and some situations demand rapid action by individuals, many strategic choices affecting long-term survival benefit from the enhanced quality of collective deliberation compared to individual decision-making. The cooperative social structure also supports care for injured, ill, or very young and very old individuals who cannot fully contribute to immediate survival activities. A person recovering from injury might not hunt or gather effectively, but can still teach children, make tools while seated, process foods, maintain fire, contribute to group discussions and decision-making. Young children cannot yet provide substantial material contribution, but they are learning, building the skills they will need as adults, and the group investment in their development pays off when they reach productive maturity. Elderly individuals past their physical prime still possess vast accumulated knowledge about rare events, successful strategies from past challenges, environmental patterns across many decades, and they serve as teachers and advisors. This care for non-maximally productive members, supported by surplus production from productive members and by social norms about sharing and support, increases group survival rates and maintains cultural knowledge across generations more effectively than systems where only the immediately productive receive resources. A parent sits with a child near the shelter as evening settles across the landscape. They talk about the day's gathering trip, but the conversation extends beyond simple reporting of what happened. The parent explains why certain plants were chosen and others avoided, describing subtle differences in leaf shape and stem texture that distinguish edible species from toxic lookalikes. The parent describes what to do if ever uncertain about a plant's safety, the careful testing procedure starting with tiny amounts, the signs of poisoning to watch for, the timing required to confirm safety. The parent tells a story about someone from generations past who didn't follow these precautions and suffered severe illness. a cautionary tale that encodes important safety knowledge in memorable narrative form. This conversation transmits detailed, complex information that observation alone could never fully convey, demonstrating how language dramatically expands the range and precision of knowledge that can pass between individuals. Language enables teaching of skills and knowledge that cannot be directly observed because they involve invisible mental processes or abstract concepts or situations not currently present. Explaining how to read tracks involves not just showing tracks but verbally describing what different track patterns mean, how to infer animal size from measurements, how to estimate time since passage from track freshness, how weather affects track preservation, how to distinguish tracks of similar species. Much of this knowledge involves interpretation and reasoning that doesn't manifest in directly observable behavior during tracking. A tracker following an animal might look successful to an observer, but the tracker's internal knowledge about what signs they're reading and what those signs indicate remains invisible unless explained verbally. With language, the tracker can make that reasoning explicit, describing what they notice and how they interpret it, transmitting understanding rather than just behavior. The precision of language supports detailed transmission of complex procedures involving multiple steps, careful timing, proper sequences, and conditional variations. Explaining how to process certain toxic plants to make them safe might involve instructions like, first remove these specific parts, then soak in running water for this duration, then cook until this texture is achieved. But if starting with dried rather than fresh material, adjust soaking time accordingly, and if bitter taste remains after cooking, the process isn't complete. This level of procedural detail, including conditional variations for different circumstances, becomes extremely difficult to transmit through observation alone, because a learner would need to observe many instances covering different circumstances to extract all the information, whereas verbal instruction can convey the complete procedure, including variations in a single teaching session. The efficiency gain is substantial, compressing learning that might require years of observation into hours of instruction. Language capacity becomes especially critical for transmitting knowledge about rare events or situations that learners haven't yet encountered and teachers may not be able to safely demonstrate. Teaching about dangerous animals, poisonous plants, environmental hazards like thin ice or flash floods requires communicating information before the learner encounters the danger personally, because encountering such dangers without prior knowledge often results in injury or death with no opportunity to learn from experience. A child who learns through direct experience that certain berries are poisonous likely dies from that experience and thus cannot benefit from the knowledge gained. But a child who learns through verbal explanation from adults who know from ancestral knowledge that those berries are poisonous gains the survival critical information without the lethal experience. This ability to learn about dangers before encountering them personally creates enormous survival advantages, essentially allowing humans to benefit from others' negative experiences without paying the cost themselves. The mechanism requires language sophisticated enough to describe situations not currently present and consequences not currently observable. Human language capacity for this kind of precise, complex communication involves several features that distinguish it from communication systems in other species. First, vocabulary size. Adult humans typically possess vocabularies of 50,000 words or more in their native language, allowing precise terms for vast numbers of objects, actions, properties, relationships, and abstract concepts. This large vocabulary enables fine distinctions, not just plant, but specific names for hundreds of plant species, plus terms for parts, growth stages, conditions, uses. Not just animal, but specific names for dozens of species, plus terms for their behaviors and characteristics. The precision supports detailed knowledge transmission. Second, grammar. Human language uses complex grammatical structures that allow embedding multiple pieces of information into single sentences, expressing relationships between concepts, indicating time sequences and causal connections, marking conditional and hypothetical situations. This grammatical complexity enables conveying not just what happened, but when and why and under what circumstances and what might happen alternatively. Third, displacement. Human language can refer to things not currently present, to past events, to future possibilities, to hypothetical situations, to distant locations. This displacement capacity allows learning from others' past experiences and planning for anticipated future situations, extending knowledge beyond the immediate present observable environment. A hunter can describe an animal encounter that happened yesterday in a location several hours' walk away, allowing others to learn from that encounter without having been present. An experienced gatherer can warn about seasonal changes coming in several weeks, allowing the group to prepare in advance. An elder can recount events from decades past, providing information about rare occurrences like severe droughts or unusual weather that the current generation hasn't yet experienced, but might need to respond to if they recur. Language also facilitates cooperation and coordination within groups by enabling communication about plans, intentions, and goals. A group planning a coordinated hunt can discuss strategy verbally: who positions where, when to begin the approach, how to respond to different animal behaviors, what backup plans exist if initial strategy fails. This explicit coordination through language supports more sophisticated cooperative efforts than would be possible with only gestural or behavioral communication. The coordinated activities that humans engage in, from complex hunts to large construction projects to group movements across landscapes, depend partly on ability to communicate detailed plans and ensure all participants understand their roles and the overall strategy. Beyond practical knowledge, transmission, and cooperation, language supports development and transmission of more abstract cultural knowledge, including explanatory frameworks for understanding the world, social norms, and rules that govern behavior within groups, stories, and histories that preserve information about past events. These abstract knowledge systems contribute to adaptability in sometimes subtle ways. Social norms that promote cooperation, resource sharing, conflict resolution, and treatment of children support group cohesion and functionality, which indirectly supports survival success. Stories that preserve information about rare events like severe droughts or resource failures provide knowledge that helps future generations prepare for or respond to similar events, even if many generations pass between occurrences. Language makes all these abstract cultural elements transmissible across individuals and generations. The development of language capacity in children illustrates how effectively humans acquire this complex communication system. Children begin learning language from birth through exposure to speech, progressing through stages of recognizing speech sounds, then producing first words around age 1, then combining words into simple sentences around age 2, then gradually acquiring more complex grammar and larger vocabulary through childhood. By age 5 or 6, most children have vocabulary of several thousand words and can use complex grammatical structures for everyday communication. This acquisition happens without formal instruction, simply through immersion in linguistic environment, demonstrating powerful language learning abilities that extract patterns from exposure to speech. The universal emergence of language in human populations, with all groups possessing sophisticated linguistic communication regardless of environmental or cultural context, suggests language capacity is a fundamental biological trait of the species that forms part of the foundation for human adaptability. A young person learns from parents and other adults how to make cutting tools from stone, spending years practicing the techniques, gradually improving skill and consistency. The tools they produce work well, sharp enough to cut hide and meat, suitable for the tasks their group performs regularly. But while practicing, this person occasionally experiments with slightly different striking angles, different amounts of force, different sequences of flake removal. Most experiments produce results no better than standard techniques, but occasionally something works notably better. Perhaps a particular striking angle creates a longer, thinner flake that leaves an edge both sharper and more durable than usual. This young person notices the improvement, begins incorporating the new technique deliberately, eventually teaches it to the next generation as part of standard practice. The children learning tool making now learn the improved technique as the baseline, the starting point from which their own skills develop. Years later, one of those children, now an adult tool maker, discovers another refinement while working with a particularly difficult piece of stone. This second innovation builds on the first, a technique that works better specifically when using the approach the previous generation developed. Again, the improvement gets incorporated into practice and transmitted to the next generation. Over many generations, this process of inheritance plus modification creates tool-making techniques far more sophisticated than any individual could likely invent from scratch, with each generation starting from the achievement level the previous generation reached and potentially adding their own refinements. This represents cumulative cultural evolution, where knowledge builds on itself across generations rather than each generation starting from zero. The cumulative process differs fundamentally from what happens in species lacking sophisticated cultural transmission. An animal that learns through individual trial and error might develop improved techniques within its lifetime, becoming more skilled than it was when young. But if that learning doesn't transfer effectively to offspring, the next generation starts over from the beginning, rediscovering basic techniques through their own trial and error. No accumulation occurs across generations, because each generation must climb the same learning curve independently. With effective cultural transmission, each generation begins where the previous generation ended, starting their learning process with inherited knowledge that took their ancestors many generations to accumulate. They don't need to rediscover fire making or stoneworking or plant processing from scratch. They learn these as standard techniques taught by competent adults, then have their entire productive lifetime to potentially add refinements or innovations that they in turn pass along. This cumulative effect creates the possibility for technologies and knowledge systems to become far more complex and sophisticated than any individual could invent alone. Consider a sophisticated tool like a compound bow, which combines precisely shaped wood, careful heat treatment, joining of different materials including horn or sinew, string construction from processed plant or animal fibers, and refined understanding of mechanical principles about how these components work together to store and release energy efficiently. No individual starting from zero, even with high intelligence and long lifetime, could likely invent all aspects of such a tool through personal trial and error. But if one generation discovers how to select and shape suitable wood, and the next generation discovers heat treatment to increase flexibility and strength, and another generation figures out how to effectively join wood and other materials for composite construction, and another develops better string materials and attachment methods, and this knowledge accumulates rather than being lost. Then eventually the full technology emerges from gradual buildup of many small innovations, each building on previous achievements. The ratchet effect describes how cultural knowledge, once established, tends to persist across generations rather than being repeatedly lost and rediscovered. Once a useful technique like fire-making becomes part of a group's cultural repertoire and gets taught reliably to children, it remains available to that population unless something disrupts the transmission process. This stability contrasts with genetic mutations, which can be lost through random chance even if beneficial, through genetic drift or through simple bad luck in which individuals survive and reproduce. Cultural knowledge has built-in persistence through teaching and social transmission. Even if some individuals in a generation never master a particular skill, as long as some do and teach it to at least some children, the knowledge continues. This persistence allows accumulation because new generations can build on the reliable foundation of previous knowledge rather than worrying that basic techniques might disappear and need rediscovery. The accumulation rate accelerates over time as the knowledge base grows, because larger knowledge bases provide more material to combine, modify, and build upon. Early generations with minimal cultural knowledge have fewer elements to work with when innovating. Later generations with extensive inherited knowledge can recombine existing elements in new ways, apply existing techniques to new materials or purposes, recognize analogies between different domains that suggest transferable principles. The pool of potential innovations grows as the knowledge base expands because innovation often emerges from combining or modifying existing knowledge rather than from completely novel invention. Someone familiar with multiple hunting techniques might combine elements from different approaches to create a hybrid technique that works better in particular circumstances. Someone skilled in multiple material working traditions might apply techniques from hide working to bark working or vice versa, transferring methods across domains. Cumulative culture requires not just transmission fidelity that prevents loss of knowledge, but also sufficient transmission accuracy that complex techniques don't degrade across generations as subtle details get distorted or forgotten. This is where language capacity becomes crucial, because verbal explanation can specify details that might be difficult to convey through observation alone, reducing the probability of transmission errors that could cause gradual deterioration of sophisticated techniques. Teaching with demonstration plus explanation creates higher fidelity transmission than demonstration alone, supporting accumulation of increasingly complex knowledge. The teaching systems that Homo sapiens developed, with active instruction, error correction, deliberate practice opportunities, and verbal explanation of principles and procedures, provide the transmission fidelity necessary for cumulative culture to operate effectively across many generations. The benefits of cumulative culture extend beyond just technological sophistication to include accumulated environmental knowledge about resource locations, seasonal patterns, animal behaviors, plant properties, weather indicators, and countless other observations that build into comprehensive understanding of local environments. Each generation adds their observations to the inherited knowledge base, gradually refining understanding of how their environment works, when different resources become available, where to find them, how to process them effectively. An elder who has lived 70 years in a territory possesses environmental knowledge that young adults cannot match simply because some patterns only become visible across decades of observation. When that elder teaches younger generations, They transmit not just their own 70 years of accumulated knowledge, but potentially the accumulated knowledge of many previous generations that was transmitted to them. The result is environmental expertise that might represent the integrated observations of hundreds of person-years of experience, far exceeding what any individual could accumulate in a single lifetime. A young child watches adults working, playing near the shelter, while parents process foods and make tools and tend fire. The child is perhaps 4 years old, still many years away from contributing meaningfully to group survival activities, still dependent on adults for food and protection and care. This extended period of dependency might seem inefficient, a drain on group resources with no immediate return. Other large mammals reach independence much faster. A deer walks within hours of birth, begins grazing within weeks, reaches full adult size and reproductive maturity within 2 or 3 years. But this extended human childhood, this long period when children consume resources without producing them, serves an essential adaptive function. It provides time to acquire the vast amount of cultural knowledge necessary for successful survival in complex human societies operating through learned behavior rather than instinct. Human children remain dependent for 12 to 15 years before reaching full adult competence, roughly twice as long as other great apes, whose young reach independence around age 7 or 8. This extended dependency period correlates directly with the amount of cultural knowledge that must be acquired. In species relying primarily on instinct and simple learned behaviors, young animals need only master relatively limited sets of skills. A deer needs to walk, run from predators, recognize safe foods from a fairly small set of options, and find mates. These capabilities develop largely through maturation of instinctive programs with some learning through observation. Human children, by contrast, must learn hundreds or thousands of skills, facts, procedures, and concepts that have no instinctive foundation, and must be acquired entirely through cultural transmission from older, more knowledgeable individuals. The complexity of cultural knowledge requiring transmission becomes apparent when considering everything a person must know to function successfully as an adult. Detailed knowledge of dozens or hundreds of plant species, including which parts are edible when, which require processing, how to prepare them, where they grow, when they fruit or seed. Similar knowledge of animal species, including their behaviors, habitats, movement patterns, how to track them, how to hunt them, how to process them after killing. Tool-making skills for multiple tool types from multiple materials using different techniques. Fire-making and fire management skills, including finding suitable materials, starting fire under various conditions, maintaining fire, cooking, using fire for tool making and other purposes. Shelter construction techniques including material selection, structural design, site selection, weatherproofing. Social knowledge including group norms, reciprocity expectations, conflict resolution procedures, kinship relationships and obligations. Navigation skills for territorial knowledge. Weather prediction based on environmental indicators. Countless other domains of expertise, each requiring substantial learning time to reach competence. Acquiring this massive knowledge base requires extended childhood because learning takes time, especially when knowledge is complex and cumulative rather than simple and isolated. A child might learn to recognize one plant species in a few exposures, but learning to distinguish dozens of similar species with subtle differences requires repeated experience across seasons and contexts. A child might learn basic stone flaking in weeks, but mastering the technique to produce consistently high-quality tools requires years of practice. Learning navigation across a large territory requires extensive travel and experience building mental maps. Learning hunting requires not just understanding animals and tracking, but also developing physical skills, judgment about when to move and when to stay still, patience to wait through long periods of inactivity. Each domain takes time, and the total time required across all necessary domains exceeds what shorter childhood periods could accommodate. The extended childhood also allows learning to proceed gradually through developmental stages that match the child's cognitive and physical capacities at different ages. Young children can begin learning through simple observation and play, developing basic motor skills and starting to build conceptual frameworks. Middle childhood allows more systematic teaching of specific techniques, with children old enough to sit through instruction, but still playful enough that learning can be embedded in enjoyable activities rather than feeling like work. Adolescence brings increased physical capabilities and cognitive sophistication that enable learning of more dangerous or complex skills, like hunting large animals or traveling to unfamiliar territories. This staged learning progression matches the extended childhood period, allowing appropriate knowledge transmission at each developmental level, rather than trying to compress all learning into two brief windows. The delayed reproduction that extended childhood necessitates, with humans typically not reproducing until late teens or 20s rather than early teens as in other apes, represents a life history trade-off where reproductive success depends more on quality of preparation than on speed of reproduction. A species strategy can emphasize producing many offspring quickly with minimal parental investment in each, hoping some survive through sheer numbers, or producing fewer offspring with extensive parental investment in each, hoping that well-prepared offspring have higher survival and reproductive success that compensates for lower reproduction rates. Humans follow the second strategy, investing heavily in each child through extended care and teaching, betting that well-educated children who reach adulthood with comprehensive cultural knowledge will thrive and reproduce successfully enough to justify the investment. This strategy works when survival and reproductive success depend heavily on learned cultural knowledge rather than on fixed instincts, which is precisely the human situation. The extended childhood requires social support beyond just parents, because caring for dependent children for 12 to 15 years while simultaneously gathering food and performing other survival activities would overwhelm parents if they bore the burden alone. This creates adaptive pressure for cooperative child rearing, where multiple adults contribute to children's care and teaching, and where older children help care for younger siblings. Grandparents, particularly grandmothers past reproductive age, often contribute substantially to child care and teaching, their presence in the group adding significant survival benefit to grandchildren, even though the grandmothers themselves are no longer reproducing. This multi-generational investment in children's development, with knowledge transmission flowing from grandparents and parents and other adults to children through teaching and observation and practice, creates the effective educational system that allows accumulation and transmission of complex cultural knowledge across generations. The brain development underlying extended childhood shows distinctive human patterns. Human infants are born with brains roughly 25% of adult size, which then grow rapidly through childhood, reaching adult size around age 6 or 7, but continuing to develop in connectivity and organization through adolescence and into early 20s. This extended brain development period coincides with the extended learning period, suggesting that brain maturation and cultural knowledge acquisition proceed together as integrated developmental processes. The brain grows while learning, with neural connections forming and refining in response to experiences and learning, creating physical neural structures that embody cultural knowledge. This neuroplasticity, the brain's capacity to modify itself in response to experience, operates most powerfully during childhood, making early learning especially effective and important. The extended childhood distinguishes Homo sapiens from even closely related species like Neanderthals, whose developmental patterns from fossil evidence suggest somewhat faster maturation, reaching adult size and presumably independence earlier than Homo sapiens. This difference in childhood duration might have contributed to differences in cultural complexity between the species, with longer Homo sapiens childhoods allowing more cultural knowledge transmission and potentially supporting more complex and rapidly evolving cultural traditions. The investment in extended childhood represents an investment in cultural adaptation capacity, producing adults whose vast learned knowledge bases enable behavioral flexibility that substitutes for biological specialization. The group faces a challenge never encountered before. The familiar game animals that provided most of their meat have disappeared from the region. Their migration patterns apparently shifted, or their populations declined, or something in the environment changed that drove them away. Whatever the cause, the animals are gone and not returning. The group's traditional hunting strategies, refined across many generations for those specific animals in that specific landscape, suddenly have no targets. Food scarcity looms. Other species facing similar situations would either migrate to follow their traditional prey, which might not be possible if suitable territories are unavailable or occupied by other groups, or would face starvation if their biology cannot adapt to different food sources. But Homo sapiens have another option. They can solve the problem through generating novel behavioral strategies. Problem-solving capacity, the ability to generate new solutions to unprecedented challenges, represents a crucial component of human adaptability because environments constantly present situations that prior experience and inherited knowledge don't fully address. No amount of cultural knowledge accumulated from previous generations can provide ready-made solutions to every possible environmental challenge because environments are complex, variable, and sometimes present truly novel situations. The inherited knowledge provides valuable foundation and starting points, but it must be supplemented by capacity to think through new problems, generate potential solutions, evaluate which approaches seem promising, and implement novel strategies when necessary. This problem-solving capacity operates through several interconnected cognitive capabilities working together. Causal reasoning allows understanding of cause and effect relationships in the environment, recognizing how different factors influence outcomes. Understanding that animals need water, and therefore visit water sources, provides a basis for predicting animal locations, even for species never hunted before. Understanding that fire requires fuel, heat, and air provides a framework for troubleshooting fire-making failures even in unfamiliar conditions with new materials. This grasp of causal relationships allows transfer of principles from familiar to unfamiliar situations, applying understanding developed in one context to different contexts where similar causal factors operate. When facing the problem of disappeared game animals, causal reasoning might suggest looking for whatever environmental change drove them away, or considering what other animals might fill similar ecological roles and could be hunted using modified versions of existing techniques, or recognizing that changes in one resource often correlate with changes in others that might be exploited instead. Mental simulation allows thinking through potential solutions before implementing them physically, running scenarios in imagination to predict likely outcomes. When considering possible responses to the game shortage, people can mentally explore options. If we try hunting smaller, more abundant animals, would the effort required exceed the food gained? If we shift toward more plant foods, are sufficient plant resources available in our territory? If we explore new areas hoping to find different game, what risks does that involve, and what probability of success? This mental exploration doesn't guarantee correct predictions, but it allows elimination of obviously poor options without the cost of attempting them physically. And it allows focusing effort on approaches that mental analysis suggests might work. The simulation capacity emerges from ability to form mental models of how things work, and to manipulate those models imaginatively to explore hypothetical situations. Creativity in combining existing knowledge in new ways generates novel solutions that aren't simply applications of known techniques to familiar situations, but rather represent genuine innovations. When traditional net hunting techniques for large herd animals no longer work because the herds are gone, someone might recognize that similar netting principles could be scaled down for catching birds or fish, species never previously targeted. When familiar stone types for tool making become unavailable in a new territory, someone might experiment with bone or wood or shell, adapting tool-making techniques learned for one material to different materials with different properties. This recombinant creativity, taking knowledge elements from different domains and connecting them in ways not previously attempted, creates genuinely new solutions, rather than just applying memorized procedures. The larger the inherited knowledge base, the more elements exist that could potentially be recombined, which is one reason why cumulative culture and problem-solving capacity work synergistically. Trial and error experimentation provides a method for testing novel solutions when mental simulation and reasoning from principles cannot definitively predict outcomes. Some solutions must be tried to determine if they work. When facing unfamiliar plants in a new territory, people can reason from similarity to known plants and from observations of what animals eat. But ultimately, some careful experimentation testing small quantities and watching for adverse effects becomes necessary to definitively determine edibility. When trying new hunting techniques for unfamiliar animals, some actual attempts are needed to learn what works. This experimental approach requires willingness to try approaches that might fail, accepting short-term risk and effort that might be wasted in exchange for potential discovery of solutions that work. The willingness to experiment, rather than only repeating known techniques, distinguishes successful innovators and enables adaptation to truly novel situations where existing knowledge provides insufficient guidance. Flexibility in strategy selection allows abandoning approaches that aren't working and trying alternatives rather than persisting with failing strategies. Many animals show remarkable persistence in repeating strategies even when those strategies fail repeatedly, driven by instinctive programs that don't easily adapt to changed circumstances. Humans show much more strategic flexibility, monitoring outcomes of their efforts and changing approaches when results indicate current strategies aren't working. If initial attempts to hunt different animals produce poor results, people try yet other approaches rather than continuing indefinitely with unsuccessful techniques. This flexible strategy switching requires both recognizing failure honestly rather than persisting in denial, and generating alternative strategies to try when initial approaches fail. The combination creates an iterative problem-solving process where successive attempts gradually home in on effective solutions through elimination of what doesn't work and refinement of what shows promise. Social problem-solving leverages multiple minds working on challenges simultaneously, with different individuals generating different potential solutions and the group evaluating options collectively. When facing the game shortage, different group members might propose different responses. Some suggest increasing plant food gathering. Some propose exploring new territories. Some recommend trying to hunt different animals. Others think about preserving foods more effectively to reduce daily needs. Discussing these options allows the group to consider more alternatives than any individual would generate alone, to identify potential problems with various approaches that different people's knowledge and experience reveal, and to coordinate implementation of whichever strategy the group chooses. The collaborative problem-solving process creates a form of collective intelligence where the group's problem-solving capacity exceeds the sum of individual capabilities. Learning from failures, rather than simply being discouraged by them, allows unsuccessful attempts to still provide value by revealing what doesn't work, and sometimes suggesting why, which can inform subsequent attempts. If an experimental plant processing technique fails to remove toxins adequately, that failure teaches that more processing is needed, perhaps longer soaking or higher cooking temperature. If a new hunting strategy fails because it underestimated animal wariness, that teaches about animal behavior and suggests strategies emphasizing greater stealth. These lessons from failure only help if people can analyze what went wrong and use that analysis to modify subsequent attempts. This learning from failure capacity, combined with persistence to keep trying after failures, creates a system where even unsuccessful experiments contribute to eventual solution discovery. A person examines a plant growing near the camp, unfamiliar, not part of the known food repertoire. The territory is new, and learning which local plants provide food will determine how successfully the group can remain here. The plant has characteristics that suggest possible edibility. It's abundant, which often indicates plants animals can eat. Birds were observed near plants of this type, though whether eating them remains unclear. It somewhat resembles a plant from the old territory that was edible after cooking. These are positive signs but not certainties. Many toxic plants also show these characteristics. Eating the wrong plant could cause illness, potentially severe, possibly fatal. Yet discovering new food sources could significantly improve group nutrition and food security. The decision emerges to experiment carefully, starting with the smallest possible amount, prepared as thoroughly as possible, then waiting to observe any adverse effects before consuming more. This willingness to experiment, to try novel foods and techniques despite uncertainty and risk, represents an essential component of human adaptability. Without experimentation, people would be limited to resources and techniques they already know, unable to adjust when moving into new environments with unfamiliar plants and animals, unable to take advantage of resources their ancestors never encountered, unable to discover improved methods that current techniques don't yet incorporate. Experimentation drives both the initial adaptation to new environments and the ongoing refinement of techniques in familiar environments. But experimentation carries risks. Not all experiments succeed. Some fail harmlessly, wasting effort but causing no real damage. Some fail with serious consequences, injury or illness, or wasted resources when those resources are scarce. The experimental strategy must balance the benefits of discovery against the costs of failure. Dietary experiments exemplify this balance particularly clearly because food experimentation brings both high potential benefits and potentially severe risks. Finding new edible plants or animals in unfamiliar territory can mean the difference between successful colonization and starvation. But consuming toxic plants or improperly prepared foods can cause illness ranging from mild discomfort to death. Human cultures have developed sophisticated experimental protocols that manage these risks while still enabling discovery. Testing small quantities first, waiting to observe effects before consuming more, trying new foods on healthy adults rather than children or pregnant women, processing new plants thoroughly before consumption, observing what animals eat as indicators of possible safety, noting similarities to known species, starting with plants that lack warning signs like bitter taste or milky sap or stinging properties. These protocols don't eliminate risk entirely, but reduce it substantially, enabling experimentation with acceptable rather than catastrophic failure rates. The experimental approach succeeds over time because successful discoveries outweigh unsuccessful attempts in their impact on long-term survival. A group that experiments with 10 unfamiliar plants might find that 7 prove inedible or require processing methods they can't figure out. 2 are edible but not particularly nutritious or abundant enough to matter much, and 1 becomes a valuable staple food. The failures represent wasted effort and possibly some illness episodes, but the successful discovery provides ongoing benefit for as long as the group occupies that territory and gets transmitted to future generations as established knowledge. The net impact over time is positive, even though individual experiments often fail. This temporal averaging of outcomes, where successes gradually accumulate while failures are survived and learned from, creates progress through experimentation despite high failure rates. Technological experimentation shows similar patterns. When trying to work new materials or develop new tool designs or improve existing techniques, many attempts produce poor results or fail outright. Stone pieces shatter incorrectly during flaking, ruining the material. Experimental hafting methods fail to secure tool to handle adequately. New shelter designs prove less weatherproof than traditional approaches. New hunting strategies spook animals or prove unsafe for hunters. These failures waste time and materials, sometimes create danger, occasionally cause injury. But successful innovations, when they occur, provide lasting improvements that benefit current generation and transmit to future generations, justifying the costs of many failed experiments. The innovation process operates through generating variation through experimentation and then selecting which innovations to retain and transmit based on their performance. A process analogous to genetic evolution, but operating through cultural rather than biological inheritance and on much faster timescales. Risk tolerance in experimentation varies across circumstances in adaptive ways. When current strategies work adequately and resources are sufficient, experimentation rates tend to be lower because the potential benefits don't justify the risks and effort. Established techniques provide reliable results, and departing from them introduces risk of failure without strong potential gains. But when current strategies are failing, or when facing novel environments where established techniques don't apply, experimentation rates increase because continuing with failing approaches guarantees poor outcomes, while experimentation offers possibility of discovering something better. The game animals have disappeared. Increase experimentation with alternative food sources because the alternative is starvation. Traditional plants unavailable in new territory. Experiment with unfamiliar local plants because without doing so, there are no plant foods at all. This context-dependent experimentation strategy optimizes the exploration-exploitation trade-off, balancing benefits of sticking with known working approaches against benefits of discovering potentially better approaches. Social learning reduces the need for costly personal experimentation by allowing individuals to adopt innovations discovered by others without paying the discovery costs themselves. When one person successfully experiments with a new food source, others can observe the success and adopt the innovation without needing to conduct their own independent experiments with all the attendant risks. This social transmission of successful innovations means that each person doesn't need to experiment with everything. Instead, the group collectively experiments with many possibilities through different individuals trying different things, and successful discoveries spread socially while failed experiments remain isolated to the experimenters. This social distribution of experimentation costs creates more efficient innovation systems than if each individual had to discover everything independently through personal trial and error. Learning from others' failures also provides value, though humans show biases toward learning from success rather than failure. When someone becomes ill after eating a particular plant, others in the group learn to avoid that plant without needing to experience the illness themselves. When a hunting technique fails badly, others who observed can note the failure and avoid trying the same approach. This learning from others' mistakes operates imperfectly because successes are more salient and memorable than failures, and because detailed information about why something failed may not transmit as readily as information about successes. But even imperfect learning from observed failures reduces the rate at which individuals repeat costly mistakes, providing some benefit from failed experiments beyond what the experimenter alone gains. Cumulative effects of experimentation over many generations produce technological and knowledge sophistication far beyond what any individual's experimental efforts could achieve. Each generation inherits the successful experiments of previous generations as established knowledge, tries some experiments of their own, discovers occasional improvements, and passes the enhanced knowledge base to the next generation. The accumulated result of many generations of experimentation, with successful discoveries retained and failed experiments forgotten, creates knowledge systems and technologies that appear remarkably sophisticated and well adapted because they represent the filtered results of countless experiments with only the successes preserved. A casual observer might think these sophisticated systems were intelligently designed from the start, but actually they emerged gradually through cumulative tinkering across many generations, where experimental variation plus selection of what worked best produced apparent design without requiring any individual to understand the complete system from the beginning. The polar bear moves across sea ice with perfect efficiency, white fur providing camouflage against endless white landscape, powerful limbs propelling it forward with strength, thick fat layer insulating against cold that reaches 40 degrees below zero, partially webbed paws distributing weight to prevent breaking through ice and providing propulsion when swimming in frigid water. Every aspect of this animal's biology optimized for Arctic marine environment, for hunting seals, for surviving in conditions that kill most other large mammals within hours. The polar bear represents perhaps the ultimate specialist, magnificently adapted to its specific environment through millions of years of evolution that refined every detail of anatomy and physiology for Arctic success. In its environment, the polar bear outperforms humans dramatically when comparing biological capabilities alone. A human without cultural adaptations, without clothing or fire or shelter or tools, placed in the same Arctic conditions, would die of exposure long before reaching hunting success. The polar bear's fur provides insulation far superior to human skin and hair. Its fat layer stores energy and generates warmth beyond human metabolic capacity. Its strength and swimming ability exceed human physical capabilities. Its hunting instincts function immediately without requiring years of learning. In the Arctic environment where it evolved, the polar bear is simply better than humans at the basic biological level. This pattern repeats across specialist species. In their optimized environments, using only innate biological capabilities, specialists outperform generalists consistently and often dramatically. But specialization carries a profound limitation. The polar bear's adaptations are encoded genetically in DNA sequences that change only through the slow process of genetic evolution across thousands of generations. These adaptations cannot be removed or modified within individual lifetimes or even across dozens of generations. The polar bear must carry its thick fur and fat layer and specialized physiology constantly, whether currently beneficial or not. If climate change warms the Arctic, reducing sea ice that polar bears depend on for seal hunting, the polar bears cannot simply adapt culturally by learning to hunt different prey in different ways. Their bodies and instincts are optimized for one specific hunting strategy in one specific environment. When that environment changes beyond certain limits, the specialist faces extinction because its genetic programming doesn't allow the flexibility to switch strategies rapidly enough to match environmental change. Place a polar bear in temperate forest or tropical savanna, and its specialized Arctic adaptations become severe liabilities rather than advantages. The white fur that provided camouflage on ice makes the bear highly visible against brown and green backgrounds, actually hindering hunting rather than helping. The thick insulating fur and fat designed for Arctic cold cause dangerous overheating when external temperatures rise above freezing. The specialized hunting techniques for catching seals through breathing holes become useless when no ice exists. The bear's metabolism, optimized for digesting high-fat seal meat, might struggle with different prey species. Every specialization that creates excellence in Arctic conditions creates limitation elsewhere. The polar bear cannot adapt to new environments because its adaptations are biological and fixed, requiring genetic evolution to modify. And genetic evolution operates too slowly to save individuals or populations when environments change within timescales shorter than thousands of generations. The camel shows similar patterns in desert environments. Humps store fat reserves that can be metabolized for energy and water during periods when food and water are scarce. Specialized kidney function concentrates urine to minimize water loss. Specialized nose structure captures moisture from exhaled air, reducing water loss through respiration. Metabolism can tolerate larger temperature swings than most mammals, reducing need for evaporative cooling that would waste water. Wide padded feet don't sink into sand. Eyes protected by long lashes and closable nostrils defend against wind-blown sand. Every adaptation creates desert excellence. But the camel cannot suddenly thrive in Arctic or rainforest conditions if forced to migrate there because environmental change eliminates desert habitat. Its adaptations work for desert and only desert. Removing the camel from that context removes the environmental match that makes its specialized traits beneficial. Mountain goats, adapted to high-altitude steep terrain, show narrow hooves with soft pads that grip tiny ledges. Body proportions, emphasizing agility over speed. Physiological adaptations to thin air at elevation. These traits enable climbing impossible slopes where predators cannot follow and where most other large mammals cannot reach. But mountain goats struggle on flat ground where their specialized hooves and agility provide no advantage and where faster predators can catch them more easily. Their high-altitude physiology provides benefits only at elevation. The specialization trades flat ground capability for mountain capability, vertical agility for horizontal speed, making the mountain goat superior in its specific niche but inferior elsewhere. The pattern repeats across countless specialist species, from deep-sea fish with bodies adapted to crushing pressure that would die if brought to the surface, to desert lizards that thrive in extreme heat but become torpid in cold, to Arctic foxes, whose white winter coat and cold tolerance become liabilities in warmer climates, to rainforest canopy specialists adapted to life in trees but vulnerable on the ground. Each specialist shows the same trade-off: optimization for specific conditions. Through genetic evolution, creates excellence in those conditions and severe limitation everywhere else. The specialist strategy succeeds brilliantly as long as environments remain stable within the narrow range the specialization optimizes for, but becomes catastrophic when environments shift beyond that range because the genetically encoded specialization cannot adjust rapidly enough to track environmental change. Homo sapiens follow fundamentally different strategy. Human biological adaptations remain generalist, performing adequately across many environments without optimizing for any. This means humans never outperform specialists in the specialist's environment when comparing pure biological capabilities. A human cannot survive Arctic cold as well as a polar bear without cultural assistance, cannot tolerate desert conditions as well as a camel, cannot climb like a mountain goat, cannot swim like a seal. But humans don't rely solely on biological capabilities. The relevant comparison is human biology plus culture and technology versus specialist biology alone. And in that comparison, the human system proves far more adaptable because cultural and technological solutions can be invented, modified, and transmitted within timescales of years or generations, rather than requiring thousands of generations for genetic evolution. When humans encountered Arctic environments, they didn't outcompete polar bears through better biological cold tolerance. They invented cultural and technological solutions: clothing, fire, shelter, appropriate hunting strategies. These inventions emerged within centuries or millennia, creating effective Arctic adaptation far faster than genetic evolution of biological cold tolerance could possibly occur. When humans colonized deserts, they didn't evolve camel-like water storage or kidney function. They developed cultural knowledge about water sources, technologies for water transport and storage, behavioral strategies for timing activity to reduce water needs. These solutions emerged fast enough that populations survived and thrived. The same pattern repeats for every environment. Cultural and technological adaptation, operating on timescales thousands of times faster than genetic adaptation, allows human populations to match or exceed specialist performance in specialists' environments, despite having inferior biological capabilities for those environments. The flexibility advantage becomes most clear when environments change. Specialists must hope that genetic variation exists that happens to be beneficial under new conditions. and that natural selection can shift population genetics toward better adaptation fast enough to prevent extinction. Often, this doesn't happen, and specialist populations go extinct when their specific environment changes significantly. Human populations facing environmental change can respond culturally within generations, developing new strategies without requiring genetic change, adjusting behaviors and technologies to new conditions far faster than specialist genetics could possibly evolve. This flexibility creates the capacity to inhabit more diverse environments than any other large mammal, to survive environmental changes that would eliminate specialists, to colonize new territories rapidly, achieving through cultural adaptability what no biological specialization alone could match. The question that began this journey now finds its answer, not through single explanation, but through understanding how multiple factors integrate into a system where the whole exceeds the sum of parts. Why did Homo sapiens become the most adaptable species on Earth? Not through one trait, but through interconnected set of capacities that work together multiplicatively. Cognitive flexibility, enabling behavioral change without genetic evolution. Cultural learning, transmitting solutions across generations faster than genetic inheritance. Generalist biology, providing adequate baseline function across varied conditions. Social cooperation, pooling knowledge from many individuals. Technological innovation, creating artificial adaptations. Teaching systems, accelerating knowledge transfer, problem-solving capacity, generating novel solutions, and extended childhood, providing time to acquire complex cultural knowledge. Each factor contributes, but their combination creates adaptive capacity far beyond what any single trait could provide. The foundation lies in minds that can change without bodies changing. Cognitive flexibility allows trying new strategies when old ones fail, abandoning ineffective approaches, experimenting with alternatives, adjusting behavior within lifetimes rather than waiting thousands of generations for genetic adaptation. This mental flexibility operates through causal reasoning that understands how environmental factors relate, mental simulation that predicts consequences before acting, memory that stores detailed environmental knowledge across years of experience, and willingness to modify strategies based on outcomes observed. The brain functions as adaptation organ, generating behavioral variation rapidly enough to track environmental changes that genetic evolution could never match. Where genetic adaptation requires 25,000 to 50,000 years for beneficial traits to spread population-wide, behavioral adaptation occurs within years or decades, a 1,000-fold speed advantage, enabling responses to environmental challenges within timescales short enough that populations survive and thrive. Cultural transmission multiplies cognitive flexibility by allowing solutions discovered by any individual to spread throughout groups and across generations through social learning rather than genetic inheritance. Observational learning lets individuals acquire skills by watching others, rather than requiring personal trial and error discovery of every technique. Active teaching accelerates learning 3 to 5 times beyond observation alone through verbal explanation, demonstration, error correction, and structured practice. The combination means each generation inherits the accumulated knowledge of previous generations as starting point rather than beginning from zero, with cultural knowledge building cumulatively as successful innovations add to inherited base while failures fade away. This cumulative culture creates knowledge systems and technologies more sophisticated than any individual could invent alone, representing filtered results of many generations of experimentation where only successes persisted. The cultural transmission system operates both vertically from parents to children across generations and horizontally among adults within generations, enabling rapid spread of innovations throughout populations in years rather than millennia. Language capacity enables detailed transmission of complex knowledge that observation alone could never fully convey, communicating not just what to do, but why and under what circumstances and what alternatives exist. Vocabularies of 50,000 words enable precise distinctions across vast domains of environmental and social knowledge. Complex grammar allows expressing relationships, sequences, causal connections, conditional variations, hypothetical situations. Displacement capacity allows referencing things not currently present, learning from past events, planning for future possibilities, teaching about dangers before encountering them. This linguistic precision supports teaching of complex procedures, transmission of abstract concepts, coordination of group activities, and preservation of accumulated knowledge across generations with minimal degradation or loss. Language transforms social learning from behavioral imitation into true knowledge transmission, where understanding transmits along with procedures. Generalist biology provides the biological foundation that cultural enhancement extends. Omnivore digestion handles diverse foods from pure meat to pure plant diets and every mixture between. Unspecialized dentition functions adequately for many food types. Bipedal locomotion works across varied terrains. Moderate thermoregulation operates across moderate temperature ranges. Moderate sensory capabilities function adequately without extreme specialization. This generalist design means adequate performance in many conditions rather than optimal performance in one, which proves more valuable for adaptability when combined with cultural and technological enhancements that compensate for biological limitations. Clothing substitutes for specialized fur in cold. Fire substitutes for physiological heat generation. Tools substitute for claws and specialized anatomy. Containers substitute for specialized carrying structures. Each technology creates artificial adaptation faster than genetic evolution of equivalent biological specialization could possibly occur, extending generalist baseline function far beyond what biology alone provides. Social cooperation pools knowledge and capabilities from many individuals, creating collective intelligence exceeding any single person's capacity. Different individuals notice different signs, remember different observations, possess expertise in different domains. Combining their knowledge produces more complete environmental understanding than any individual achieves alone. Division of labor allows individuals to develop specialized expertise, while group maintains comprehensive skill coverage. Information sharing distributes discoveries throughout groups and across intergroup social networks, accelerating innovation spread. Collective problem solving generates more potential solutions than individuals working alone. Social support enables care for young, old, injured, maintaining cultural knowledge, transmission, and group functionality across full lifespan range. This cooperative social organization transforms groups into superorganisms whose adaptive capacity exceeds simple aggregation of individual capabilities. Extended childhood provides time to acquire vast cultural knowledge bases that adult competence requires. 12 to 15 years of dependency allows gradual skill building through developmental stages, matching cognitive and physical capacities at different ages. Learning hundreds of plant and animal species, mastering multiple tool types and techniques, acquiring navigation and weather prediction and social knowledge, developing hunting and gathering and construction skills all require extended learning periods that shorter childhoods could not accommodate. The investment in extended childhood represents investment in cultural adaptation capacity, producing adults whose comprehensive learned knowledge enables behavioral flexibility that substitutes for biological specialization. Brain development continues throughout this extended period, with neural structures forming and refining in response to cultural learning, physically embodying accumulated knowledge in neural networks that guide skilled performance. Problem-solving capacity generates novel solutions to unprecedented challenges that inherited knowledge doesn't address. Causal reasoning enables transfer of principles from familiar to unfamiliar situations. Mental simulation allows exploring potential solutions before implementing them physically. Creativity recombines existing knowledge in new ways, producing genuine innovations. Experimentation tests novel approaches when reasoning alone cannot predict outcomes. Flexibility in strategy selection allows abandoning failing approaches and trying alternatives. Learning from failures informs subsequent attempts. These problem-solving capabilities, operating on the foundation of inherited cultural knowledge, enable responses to environmental challenges that previous generations never encountered, extending adaptability beyond merely repeating ancestral solutions to include generating new solutions when novel situations demand them. The integration of these factors creates multiplicative rather than additive effects. Cognitive flexibility alone provides some adaptation capacity through individual behavioral adjustment. Cultural transmission alone provides some capacity through social learning. But cognitive flexibility combined with cultural transmission creates cumulative cultural evolution, where knowledge builds across generations, producing far more sophisticated adaptations than either mechanism alone. Adding language to this combination increases transmission fidelity and scope dramatically. Adding social cooperation and teaching systems accelerates knowledge spread and improves transmission accuracy. Adding generalist biology that cultural enhancement can extend creates broader adaptive range than pure specialization could achieve. Adding extended childhood provides time to transmit increasingly complex cultural knowledge. Adding problem-solving capacity enables innovation that keeps adaptation systems current with changing environments. The factors work together synergistically, each enhancing others' effectiveness, creating integrated adaptive system whose total capacity far exceeds what summing individual contributions would predict. This integrated system explains human geographic range exceeding any other large mammal, inhabiting environments from Arctic tundra at -60 degrees to tropical deserts at 130 degrees, from sea level to 16,000 feet altitude, from regions with 200 inches annual rainfall to regions where years pass between rain. No specialist could survive such range through biological adaptations alone because genetic evolution operates too slowly to create diverse specializations in the timescales involved. But cultural evolution operating at thousand-fold faster pace can generate appropriate adaptations for each environment within centuries or millennia, enabling colonization of the entire planet within roughly 50,000 years from initial expansion beyond Africa. Each new environment encountered prompts innovation of appropriate technologies, development of relevant environmental knowledge, modification of strategies to local conditions, all occurring through cultural and behavioral change without requiring genetic evolution. The human adaptive system transforms relationship between organism and environment. For specialists, environment determines fitness through matching between genetically encoded traits and environmental demands, with poor matches leading to extinction and good matches leading to survival. For Homo sapiens, fitness depends less on genetic matching to environment and more on cultural capacity to generate appropriate behavioral and technological responses to environmental demands. The environment still determines survival, but through different mechanisms. Not through selecting genetic variants, but through selecting cultural variants, and doing so within timescales where populations can respond through learning and innovation, rather than dying out before genetic adaptation occurs. This makes human adaptation fundamentally different in kind, not just degree, from other species' adaptation, representing transition from genetic to cultural evolution as primary adaptive mechanism. The success of this adaptive strategy appears in human population growth, geographic spread, and persistence through environmental changes that eliminated other large mammal species. Populations expand into every habitable environment, and many seemingly uninhabitable ones that become habitable through cultural and technological solutions. Groups survive climatic shifts, resource fluctuations, and environmental changes that required adaptive responses faster than genetic evolution could provide. The flexible species thrives not through being strongest or fastest or best adapted biologically to any particular environment, but through being most able to adapt culturally to whatever environment encountered, most able to generate and transmit solutions to environmental challenges, most able to modify behavior within time scales matching environmental change. This flexibility, emerging from integrated system of cognitive, cultural, social, and biological traits working together, represents the answer to why Homo sapiens became Earth's most adaptable large animal, capable of adequate performance in virtually any environment through unique combination of modest biological generalism plus extraordinary cultural and cognitive capacity for rapid behavioral adaptation.